Hi, welcome to chapter 1, the Copernican Revolution. I wanted to do a screen slideshow, please. Is it going to work? Okay, so welcome to chapter 1, the Copernican Revolution. So here we have a carving of an ancient carving of what they used to think. My Zoom controls are in the flipping way. So this is sort of like how they used to think the celestial sphere was. So this is an ancient carving of what they thought the sky was. So in chapter 1, we're going to talk about the motion of the planets, the birth of modern astronomy, the laws of planetary motion, and then Newton's laws. So pretty cool. We're going to talk about geocentric models, meaning the Earth is at the center of the universe. We're going to explain retrograde motion of the planets around the sun. We're going to talk about scientific developments for Copernicus, Tycho, Galileo, and Kepler. It's Tycho Brahe. I don't know why his whole name's on it. It's like his first name's in there. Anyway, okay. We're going to talk about Kepler's laws of planetary motion. We're going to talk about how astronomers measured the true size of the solar system. That's an interesting kind of story of science. And then we're going to talk about Newton's laws of motion, blah, blah, blah. All right. So here's our vocabulary for section 1. I'm going to talk about retrograde motion and some other things here. So over the night, so what ancient astronomers saw when, because they didn't have a lot of lights and stuff, so they had a really good view of the sky. So over the night, they saw the stars move through the sky. Over a month, they saw the moon pass through all of its phases in front of the stars. Over a year, it saw the sun moving along the ecliptic. And then it also saw other bodies in the sky. They were able to see Mercury, Venus, Mars, Jupiter, and Saturn. But their motion was kind of hard to understand, and figuring it out changed our worldview, which is kind of cool. So planets, like the moon, only reflect sunlight. So they don't actually create their own light. They only reflect sunlight. So a logical conclusion would be that if they're brighter, then they're closer. It's kind of a logical conclusion for that. But wait, Mars, Jupiter, and Saturn are always brightest during the retrograde portions of their orbit. So you logically conclude that they could be potentially closer to the planet if they're brighter during retrograde, which we're going to talk about in a second. So this challenged ancient astronomers. And why would a planet change its brightness? So the sun, moon, and stars all have simple motions in the sky consistent with an Earth-centered system. Planets, though, are weird, and they move with respect to the fixed stars. They can change brightness. They can change their speed. They have this weird retrograde motion, which we're going to talk about, and they're difficult to describe if you're using an Earth-based system. So here we have a planet coming in. I'm guessing it's Mars, but I'm not sure. Planet coming in. So November 1st, it's here against the background sky. There's Leo and Cancer. So we can see it here on November 1st. December 1st, it's about here. January 1st, it moves here. February 1st, it looks like it's swooping back on itself. March 1st, April 1st, and then it heads back out again. So these are kind of the retrograde motion. So that's what happens when a planet is in retrograde. Oops. So it's got this weird backward motion that we see. It kind of loops back. Is my mouse just not responding? Okay, so we're going to, okay, so the retrograde motion was confusing to ancient astronomers. So the geocentric model of the universe, where the Earth is at the center, Aristotle, who died in 322 BC, he developed the early model of the universe. It was geocentric, with the Earth at the center of the universe and all other bodies rotating around it. Aristarchus, so I can never say his name. Aristarchus, sorry, of Samos, in somewhere around there. He proposed that the Earth and the planets orbit the sun, but no one listened to him because Aristotle's influence was too strong. Doggone it. Anyway, so Ptolemaeus, also known as Ptolemy, constructed the best geocentric model that we have. It's called the Ptolemaic model. So basically, the basic geocentric model shown here with epicycles, it's used to explain that planetary motion. So to explain retrograde motion, each planet was thought to follow a small circular orbit, an epicycle, about an imaginary point and traveled in a larger orbit or the deferent. So Earth is at the center of the universe. We got a planet going around here, but sometimes it goes backwards. And so they put these little epicycles in there. So lots of epicycles were needed to accurately describe the motions of the planets, especially retrograde. This is Ptolemy's model. So to achieve a model that worked, one that would predict behavior, Ptolemy needed 80 different cycles. It was very, very complex because once again, with science, we're trying to predict behavior. So he had all these little epicycles with Earth at the center and the moon, and then the sun was there. Okay. So epicycles with a deferent and orbit around Earth accounted for the retrograde motion of the planets. With some tweaking, it also explained the changes in brightness, but it was also very, very complex. So now, too, we're going to explain how the retrograde motion actually arises from the orbital motions of the planets around the sun. So the Ptolemaic model survived and for almost 1,300 years. So in the 16th century, so Aristotle came up with that whatever, and Ptolemy built that thing. So a whole bunch of time later. So 16th century cleric Nicholas Copernicus rediscovered that guy's heliocentric model. He didn't publish his work though. So it was 1543 when he died. And the reason why he didn't publish it was the church. So anyway, just kind of weird. So the Copernican revolution, though, was this critical realization that the Earth is not at the center of the universe. So he asserted that the Earth spins on its axis and it orbits the sun, which accounts for star motion, the moon, and the sun, and the retrograde motion of the planets then becomes simple. So in a heliocentric or sun-centered model of the solar system, we can easily describe the motion of the planets without any excess complication. So if we look here, we've got the sun at the center, we've got the Earth here, and here we have Mars. So Earth is at position. My zoom controls are still in the way. Why do they sometimes hide and sometimes they don't? Wait. There you go. Thank you. So Earth's, here we are, orbit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And here is Mars, 1, 2, 3, 4, 5. Okay, so when we were at 1, and we're looking at Mars at 1, it appears to be here in the background sky. When we're at 2, Mars is at 2. Here's where it appears to be. We're at 3, 3, 4, 4, 5, 5. Now, if you'll notice at 6, we're lined up and it's right there. At 7, we pass it. So we're going faster. And now that is why it appears to go backwards. So it actually hasn't gone backwards. It's here. But when we look at it through the night sky, it appears that it has. So this is like at 5 and it's at 5, and then we see it here. When we move to 6, it's at 6, but we see it here. So that's why it looks like it loops back. If you need to trace this to get your brain to work, because I didn't explain it as good as I could have. But anyway, we're going faster than that planet, and so that's why it appears to go backwards. Sort of like if you're in the car and the car next to you moves or something, you're not sure which direction you're going. Anyway, so here's a bigger view of it. So Mars actually 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But as we're passing it, it appears to loop back in on itself. Okay. So Earth's orbit is faster than Mars. Sometimes Earth catches up to Mars and then zooms past. Mars appears to move backwards compared to the background stars because we are overtaking it and surpassing it, kind of like a car on a highway. And this happens when Earth is closest to Mars, which is why Mars appears brighter. So the birth of modern astronomy. There's no vocabulary in this section. So here is a painting of Galileo Galilei and Johann Kepler. And they were both very important to astronomy. So describe the scientific developments that led to modern view of the solar system from these guys right here. So Um, Galileo Galilei was an Italian mathematician and a philosopher. He's the father of experimental science. He used his telescope and performed scientific experiments to test his ideas. The telescope was invented in 1608, having it was more like an eyepiece for sailors kind of thing. So, having heard of the design, he decided to build his own in 1609. It was used for viewing the night sky rather for sailing. So the spyglass, whatever, it was invented in 1608, but he used it for the sky in 1609. Although those sailors were looking at the stars with that, but he was the first one who like scientifically did stuff. So, because those sailors were looking at everything. Anyway, okay, observations of that Galileo made with his telescope. He looked at the moons, mountains, valleys, and craters. He looked at sun's imperfections and how it rotates. He also burned the back of his eyeballs by doing that. Don't ever, number one rule of astronomy is never look directly at the sun, especially through astronomical equipment. Anyway, he also discovered Jupiter has moons. That's why they're called the Galilean moons. And he also discovered that Venus has phases, kind of like the moon, because it's interior and we can see the shadow side. All right. So the phases of Venus are impossible to explain in an Earth-centered model. This kind of makes my head hurt a little bit. So here we have Earth at the center, and here is Venus, sort of the sun is the Venus is between Earth and the sun, and we see all these different phases, but it's weird. But if we have the sun at the center and Earth on the outside, then we can explain sort of the phases, because we just see a little crescent here when it's directly like between us, and then we see all those. Anyway, you can actually, if you look at Venus, you can see the phases. So there's no full phase possible with this model, so you cannot see, you can't see the full face of Venus with this one, because it's new. You're seeing the shadow side. It's new. You're seeing the shadow side. But with the sun at the center and the Earth, you can see full Venus in this regard. Okay. His observations were a contradiction to the general belief that the heavens were constant and immutable. So he was in trouble. So he published his findings in 1610. In 1616, he was judged and ordered to abandon his astronomical pursuits. He was placed under house arrest in 1633 until he died. And then the church finally forgave his crimes in 1992. Oh my gosh. So anyway. So let's see, there's more stuff here. Describe the scientific developments. Okay, Copernicus had the heliocentric theory. Tycho had detailed observations. I think we're going to talk about that next. Yes. Galileo was the first one to use the telescope for the sky, and Kepler was a theorist who discovered the 3 laws of planetary motion. Okay, that's what we're going to cover next, I think, although it said review. All right, here's our vocabulary. Okay, so Johann Kepler was a mathematician and an astronomer. He discovered a simple set of laws that accurately describe the motion of the planets. So Galileo used observation with his telescope to create and refine his theories, but Kepler was a pure theorist. Kepler used observational data from Tycho Brahe, who was his employer. Tycho Brahe was arguably one of the greatest observational astronomers ever lived. Quote from the book. He almost lost part of his nose in a sword fight, though, or he did lose part of his nose in a sword fight, though, over a scientific disagreement. So he's kind of a jerk. And he had to wear this brass nose. Anyway, so I always make this joke in class. So if we have experiment versus theory, Johann Kepler was all theory, which is like Sheldon, and then Galileo was more experimental. Like, why can't I remember his name? I can't remember his name. Oh, that's terrible. Okay, so Kepler's law. So after working with Tycho Brahe's observational data, and then abandoning Copernican's circular model of planetary motions, Kepler discovered 3 laws of planetary motion. So Copernicus thought that the orbits of the planets were circular and perfect. Tycho Brahe did all these detailed observations which he wouldn't let Kepler have the data until like he didn't get it till after he died or something weird like that. The book will tell you more information about. There's some dirt in the book, right? Some gossip. Anyway, so when Kepler discovered that they are ellipses and not circles, then he was able to discover these three laws of planetary motions, which I'm going to explain, and they're kind of confusing. But the first law, the orbital paths of the planets are elliptical with the sun at one focus. They're very close to circular, though. And if you remember, an ellipse is just a squished circle, basically. Second law, an imaginary line connects the sun to any planet, sweeps out equal areas of the ellipse in equal time frames, which is kind of strange. That one's going to be hard to understand. The third law, though, the square of the planet's orbital period is proportional to the cube of the semi-major axis. Oh my gosh, that is an equation written out in English. So we're going to explain that in a little bit. So we're going to look at Kepler's laws of planetary motion. So if you remember this experiment from grade school, if you have a string and two pins and you put the two pins through the string and then you stretch it out with a pencil and you can draw an ellipse this way. Kind of cool if you wanted to do that for extra credit points, email me your stuff. So planetary orbits are ellipses with the sun at one focus. This is extremely squished. Like I said, most of the planetary orbits are almost circular. So here is the focus or one of the pins. The sun is at one of the pins, and then the planet will sweep out. So this is where your planet would be. So your planet would sweep out. So there's perihelion, the closest, and aphelion, the farthest. So this is, we learned last time that we are closest to the sun during northern hemisphere winter. We're farthest from the sun in northern hemisphere summer. Okay, so that's planetary orbit. So the next one, that's Kepler's first law. The first law, an ellipse is a flattened circle. Focus are the special points along the major axis here. An ellipse is a plane curve surrounding two focal points such that for all points on the curve, the sum of the two distances of the focal points is constant. Basically, what this means is the string is unchangeable. It's not a rubber band, it's just a string. And so it's the same length, even though you have it in different positions, is all that means. Therefore, you can draw it with a string. The string size remains the same as you go around the ellipse, as you can see here. So these will change, right? And when your pencil's over here, you've got this comes up and over here, but the length of the string doesn't change, is what that means. Okay. So a major axis is the axis along the two foci. The semi-major axis is half the length of the long axis. Eccentricity is equal to the distance between the foci. Blah, 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 blah. Eccentricity just means how squished it is. Ellipse anatomy, that's useful for an astronomer. Planetary orbits are ellipses. The sun is at one focus. When a planet is closest to the sun, it's perihelion. When it's farthest away, it's aphelion. Planetary orbits in our solar system are very close to circular, though. Okay, and here's this picture again with more information. Okay, so this is the second law that makes my brain hurt a little bit. When a planet is closer to the sun, perihelion, it moves faster. When a planet is farther away from the sun, at aphelion, it moves slower. And it has to do with this weird area, adding the area, and I'm just, this is the same period as this. So we whip around the sun when we're close to it, is all you need to know for that one. So it sweeps out equal areas in equal time. This confuses me because the arrows don't go in the same direction. Anyway, so these are the same. The planet is moving slower here. So this is the same time frame as the faster moving planet here. That has to do with gravity. The third law relates orbital size to orbital period. And this is one of those essential things that math helped us understand the solar system and the universe a little bit better. So a period is the time needed for the planet to make one circuit around the sun. So for us, it's 1 year. The third law says the square of the planet's orbital period is proportional to the cube of its semi-major axis. The square of the planet's orbital period is proportional to the cube of the semi-major axis. Blech. But it's kind of weird because we define the average distance between the Earth and the sun as 1 astronomical unit. So that's our distance. And we have 1 year. So we have 1 squared equals 1 cubed. How cool is that, right? All right. But that's actually kind of neat. The noticing that it's an eclipse, this is just sort of it's an equation of an eclipse kind of thing. Um, so the square of the period of the planet's orbital motion is proportional to the cube of the semi-major axis. What that means is we are now able to calculate some things. So if the Earth is 1 astronomical unit away, we just defined it. We as scientists can define our measurement thingies, right? We can distance is measured in astronomical units, light years, miles, kilometers, meters, inches, millimeters, all sorts of stuff, right? So we have defined this unit of astronomical units. So Earth is at 1, the orbital period is 1, our eccentricity is shown here. And then if we take our p squared and a cubed, we get 1 because 1 divided by 1 is 1. And then we are able to sort of calculate the astronomical units of each of the other planets because of their orbital period. Okay. And so we are able to figure out how far away they are from the sun. So because we can figure out what their orbital period is, then we can figure out what that p squared equals a cubed kind of thing. So if we know the p, we can figure out the a. It's basically what that means. Whew. Okay. But that's giving us the distance from the sun in astronomical units. At the time when they figured this out, they didn't know how big an astronomical unit was. So in the 1960s, no, I don't remember when they did it. So they used radar, maybe it's shown in the slides. They used radar, which is radio detection and ranging. So radio waves are transmitted toward an astronomical body, and the returning echo waves indicate the body's direction and distance. So instead of using the relative positions, the astronomical, the AUs, that's the relative positions from the astronomical unit. Sorry, we now have a physical measurement in kilometers. So we can multiply the round trip time the radar signal takes and divide it, and you get the distance to the planet. So here we have dimensions of the solar system, how we unraveled this. So the distance to the Earth to the sun is an astronomical unit. Its length may be measured by bouncing a radar signal off Venus and measuring the signal's travel time. So here at Earth, at 1 astronomical unit, Venus, we calculated with the p squared equals a cubed. We knew it's p, so we could figure out its a was 0.7 astronomical units. And then we take a radar, bounced radio waves off of it, and we figured out basically that there are 0.3 astronomical units between us, but we know the speed of we know the speed that the radio waves are traveling, and so that actually gives us detection in kilometers or miles. So before we had this unit that we made of astronomical units, and we could figure stuff out, but now we know what the actual measurement is in kilometers or miles. So we used, anyway, we were able to do that, which is, I think it's kind of cool. So Newton's laws. So Newton was a British physicist and mathematician. He died in 1727. The theory is, I don't remember if it's in this book or what, but he somewhere in my studies, he died a virgin. So he was the one who invented calculus. So if you don't like him, I can kind of understand that. So Kepler's laws were discovered empirically or from analysis of observational data rather than a theory or a mathematical model. So the earlier models described the motion of the planets, but Newton wanted to know why it happens. So Newtonian mechanics was developed. It's a deeper understanding of how all objects move and interact with each other. He created 3 laws of motion based off of Kepler's 3 laws of planetary motion. So here they are. I think we're going to go through them fast. So Newton's three laws of motion, if you went through physics, you probably just spent way too much time on this. So Newton's laws of motion explain how objects interact with the world and each other. So Newton's first law, an object at rest will remain at rest, right there. An object moving in a straight line at a constant speed will not change its motion, right there, unless it's acted on with an external force. So boom. So an object at rest will stay at rest. An object in motion will stay in motion unless acted on by a force. Inertia, the tendency of an object to keep moving at the same speed in the same direction unless acted on by a force. That's the term. These are just physics terms. Mass, the total amount of matter that an object contains, which is different from weight. The greater an object's mass, the more inertia it has, or the greater force needed to change its motion. So if you think a big semi and a teeny tiny little smart car. So the rate of change of velocity of an object, speeding up, slowing down, or changing direction, we call that acceleration. So that leads us to Newton's second law. When a force is exerted on an object, its acceleration is inversely proportional to its mass, meaning that when it says inversely proportionate, that means that there's some sort of fraction or division. So the greater the force, the greater the acceleration. The same force but less mass, the greater the acceleration. That's what it means. For all you nerds out there, this is F equals ma, basically that. Newton's third law, when an object A exerts a force on object B, and object B exerts a force equal and opposite forces on those. So that's basically sort of leads us to gravity. So forces act either instantaneously or continuously. I'm going through this rather quickly. I'm sorry. Read your book. Newton discovered gravity. So Newton hypothesized that any object having mass exerts an attractive gravitational force on all other massive objects. The more massive the object, the greater the gravitational pull. So you are actually pulling the Earth towards you, but the Earth is so much bigger that the Earth, it doesn't really notice. So on Earth's surface, the acceleration due to gravity is approximately constant and directed toward the center of Earth. So if a guy throws a baseball, it will sort of follow this parabolic path. So it will go up, but there's always this pull of gravity down. That's why he is throwing it up, but gravity sort of overtakes it and then it comes back down to Earth. So for two objects, gravitational force is proportional to the product of their masses divided by the square of the distance between them, blah, blah, blah. Once again, this is just math written in words. So here we have a mass 1 and a mass 2, and the gravitational force between them is dependent upon how big they are and how far apart they are, basically, is what that is meaning. How big they are and how far apart they are. So every particle in the universe attracts every other particle with a force that is directly proportional to the product of their masses. Directly proportional means it's on top of this fraction. The product of their masses and inversely proportional to the square of the distance. So the greater the distance between them, the smaller the force is going to be. That's what that means. When this goes up, this goes down. When this goes down, this goes up. That's what inversely proportional means. When these go up, these go up. That's what directly proportional means. Okay. Anyway, so the gravitational pull of the sun keeps the planets in orbit. So the planet actually is just kind of moving in this direction, but the sun pulls it around, which makes it orbit the thing. Okay. Just as Kepler updated Copernicus's laws, Newton updated Kepler's laws. So Kepler's first law of planetary motion, the orbital paths of planets are elliptical with the sun at one focus, now becomes, with Newton's addition, the orbit of the planet around the sun is an ellipse having a center of mass at the planet-sun system at one focus. Because the sun is so massive, this point is very close to the center of the sun. Okay, so basically, it's kind of like this. Massive objects actually orbit around their common center of mass. If one object is much more massive than the other, the center of mass is not far from the center of the massive object. For objects more equal mass, the center. Okay, so these two are sort of equal masses, and so the centers between them. This guy is a lot bigger than these two, and so, yeah. the center of mass has to be closer to, wait, I'm so confused. All right, I don't think that makes sense anymore, but don't worry about it. That is not something you need to worry about. You can read the book if you would like more, but there's something's not jiving with my brain at the moment, which is fine. Okay, so there's consequences to Newton's laws. Let's see, we got a planet and a planet, and they're changing masses, and this, okay, so it's okay. Basically, what it's saying is things with greater mass will exert more gravitational pull and things will act accordingly. So if we were to have a big old, whatever. All right. This is demonstrating how they were able to use these concepts to discover the black hole at the center of the Milky Way. So over about a 10 or 20-year period, this one scientist was using radio observations of the center of the Milky Way and was tracking all of these stars and was tracking these stellar motions. And they had 5 or 6 stars or whatever. I don't know how many there are, 7 maybe stars. And they were able to calculate the mass at the center. Okay, so oops, if we go back here, right here. So mass 1, mass 2. So mass 2 is the star, right? And so they know sort of kind of all this stuff and they're able to tell stuff. Anyway, they're able to calculate the mass. So they were able to calculate the mass of the object at the center of the Milky Way. And it turns out it's a black hole that's 4,000 times, 4 million times bigger than the sun or something like that. Anyway, so Kepler's third law in mathematical form, basically the geometry of an ellipse, that should have a parentheses at the end. So the period squared in Earth years is equal to the distance in astronomical units cubed. And since Newton discovered the mathematical formula that predicts the observations made by earlier astronomers, we can now calculate the mass of an object. So we can put this in here and now calculate the mass, which is kind of cool. We can do distance if it's close. We can do distance with just math, with that triangulation stuff and parallax. And now we have an ability to watch motions and discover how much mass is in an object, which is pretty cool. So we have Newton's first law of motion, second law of motion, third law, and then the law of gravity is here. So first models of the solar system were geocentric, but they couldn't explain retrograde. Heliocentric does explain retrograde really well. Galileo's observations supported heliocentric model. Kepler found he found the ellipse and was able to do all these wonderful calculations. Newton then explained some other stuff, and now we are able to figure out masses of objects. So far, just from math, we're able to figure out the distance to some nearby objects that we can see kind of shifting in the sky depending on where we are. We were able to take observational data and figure out that the sun is at the center of the solar system. We were able to figure out ellipses and figure out planetary motions, which allowed us to do some initial discoveries on distances. And then we used radar to find the actual distances. And then Newton did his magic stuff. And now we're able to figure out mass. So we have figured out a whole bunch of stuff, which we didn't know just from math. Yay, math, go math. Okay, that's it for this chapter. I will see you soon. And thank you. Have a wonderful